Okay, so welcome everyone. It's a pleasure to introduce you to Alastair, Dr. Alastair Basden from the Durham University. He's a senior researcher and the associate in the Department of Physics, and he is working with astronomical active optics, including real-time control systems and simulations, as well as the design and bench work. He's going to tell us something about the AO real-time control, and let's give the talk.
Okay, can you hear me? Yeah, good. Well, thank you for coming. So yeah, as was introduced, this is me, Alastair, from Durham University. That's just a picture of Durham Cathedral, which is a very nice building. So if you're ever in the area, then do pop by. So I'm going to talk a little bit about real-time control systems and what they are, what sort of considerations you need to give if you're designing one of these. Then I'll introduce DARC, which is our system. Talk a bit about it. Talk about how it's implemented on CANARY, which is an AO system that sometimes goes on a WHT, just over the water, and relevance of this for the AO system for grant account. Right, so what is real-time control? It's a process of taking wavefront sensor images, and you see here this is just some on-sky images that I took last week with CANARY, 4 natural guide stars, 4 laser guide stars, and a figure sensor. So it's converting those images that come from cameras to DM demands. There's a DM shape that we add on sky at some point. Just a random one. So, our brief history of real-time control. So in the 1980s, there wasn't very much going on. It was all military, and who knows what that was. But in the 90s, our basic FPGA and DSP systems for doing real-time control. In the 2000s, the trend tended towards CPU-based systems. This was helped with the arrival of multi-core processors in about 2004, something like that. And then, since then, this decade, we've had the arrival of many-core systems, including GPUs. And I know here, CANARY was actually the first AO system to use a GPU on Sky in 2010. It actually slowed it down, but it was beside the point, I think. So, computational procedure for real-time control. You calibrate an image. You can compute the center of gravity in each structure, assuming it's a Shack-Hartman system. You reconstruct the wavefront. You project that onto a DM space. Right? Sounds easy. There are, of course, many considerations. Okay, so you could put all that together in a very simple script, whether it's MATLAB or anything else, Python. But that's only a small fraction of the story. You've got to consider reliability. Some of these systems, you have the loop closed for a whole night. Latency. You want your latency to be predictable. I'll talk more about latency later on. Flexibility. If you've got new algorithms you want to test, you need to be able to put them in. You want your system to be configurable. You need to be able to handle errors. You don't want your telescope operator to have the system crash and not know what's gone wrong. You need user interfaces. You need to be able to use the system. It needs to be synchronized. You need to think about clients, how you're going to do your auto-guiding, how you're going to find out where your telescope is pointing, telescope status, optimize the AO for air mass and all that sort of thing. So the traditional approach from the late 90s and early 2000s, I suppose, was to use DSPs, FPGAs, and custom hardware. So you would typically, systems from that era would use an FPGA to read out the cameras, and would do pixel processing, so calibration. There'd be custom interfaces between the cameras and the DMs. So, for example, the ESO Sparta system, which was developed from 2003, 2004, 2005 onwards. It's now being installed, well, it's been recently been installed for VLT on Sphere, the XAO system, and it's being installed in the AOF. However, ESO now recognised that this was the wrong approach, using FPGAs and so on, because it's led to a system that that's not adaptable. They can't really change the system, and it's very expensive. If someone wants to use their AO system, you're talking a lot of money, £100,000, just to get the basic equipment set up. A lot of expertise is required. You need to use specific IDE design environments, VHDL through FPGAs. You're locked into specific vendors for those. Spare parts, of course, becoming difficult to obtain, even though they're only just going on Sky with these systems. Some of the parts they use are now no longer manufactured. And I can say that because we helped, at Durham, we helped design part of their Sparta system. So, commodity PC hardware. You have nowadays, you have multi-core CPU servers. They can be programmed in C and high-level languages. Expertise which is widely available. Plenty of C programs around. They're easy to replace. If your computer dies, you can just buy a new computer, usually with improved performance because the CPUs get faster all the time. And they're also widely available. There's low barrier to adoption. You can just go buy one of these very quickly and install your software on it, in theory. So, DARC. DARC is the Durham AO real-time controller. It's a PC-based real-time control system. It was initially developed, has a bit of an interesting history. It was initially developed as a backup solution for CANARY. I'll talk about CANARY in a minute. And that was in case a commercial offering that CANARY paid about £200,000 for failed. And actually, this commercial system did fail, didn't make it on Sky. We had to change systems a couple of months before we went on Sky to use DARC, which, with hindsight, was a very good decision, one that we should have made several years before. So algorithms have been added continuously. We're always adding new algorithms that we test on Sky with CANARY. We tested a new one just last night, new reconstructor, and a closed loop on it. ELT-scale performance has been investigated and developed. We have a system that is now suitable for ELT-scale problems. It has a modular design, so it's not specifically for one AO system. It works with CANARY, but it will work with any other system that you want to use it for. It's got expansion built in. So the real-time core, which I'll cover in a bit, is written in C. Other components are mostly C and Python, though it's modular, so you can develop in whatever language you like. There's a GPU pipeline available, and it's open source, so you can go and download this software from SourceForge. So, CANARY. I said I'd talk about CANARY a little bit. It's an ELT AO demonstrator instrument on the WHT. It's been used in plenty of AO modes, starting with SCAO, multi-object AO, laser tomographic AO, ground layer AO. Has 3 natural guide stars, 4 Rayleigh laser guide stars, and you can just see on the picture here the Rayleigh laser being launched. Has a truth sensor, which is an on-axis wavefront sensor, which we use to verify performance, as well as having a STREL, a PSF, and an infrared PSF. We have this optical truth sensor, and a figure sensor, which is used to actually look at the shape of our deformed mirror so we know what that's doing. It's a low to mid-order correction system. We have 60 centimeters of apertures at the moment. Next summer, we'll be decreasing the aperture size to somewhere between 30 and 40 centimeters. So in CANARY, we have 4 natural guide stars. These are all based on Andor Ixon cameras. You can see a picture of one there on the left. Fairly basic, fairly standard cameras. You can just buy them off the shelf. One thing we have done with these cameras is we've borrowed an ESO Sparta interface, which converts the proprietary Andor pixel stream into serial FPDP, which is an industry standard protocol widely used in military applications and so on. And that gives us access to the pixels as they come from the camera. We don't have to wait for a whole frame to arrive at the computer. We can access these pixels as they arrive. We have our 4 laser guide stars. These are, since they're Rayleigh, we send a pulse of light up into the air. Once it reaches a certain height, we open the shutter of our camera to get the backscatter light. Pulse propagates a bit higher, we should close the shutter. And we pulse these lasers at about 10 kilohertz, so we have this shutter opening and closing at about 10 kilohertz. Now, of course, you can't do that with a mechanical shutter, so we have to use special detectors which are able to do that electronically. So in 2012, 2013, we used a fairly custom system. It was a controller built by SciMeasure in the States and a CCD that had been made by Lincoln Labs. We developed our own custom interface for that controller, so again we could have access to the pixel stream. That chip, well, one chip died. We had to send that for repair and buy a new chip. And then just this summer, the controller died, and we thought, well, we've had enough of this. It was an awkward system to use. We're not going to use it again. And it was with too short notice for our next on-Sky run. So we then used a cheap, off-the-shelf Bobcat camera. See there, they're about £2,000 each. Never really meant for lab. They're not meant for going on sky. Fairly high readout noise. But we discovered that these, by mistake, we discovered that these are actually able to gate, to do the laser range gating, the electronic shutter. So we used one of those in June, in July on sky. During which time we have been in the process of procuring an Ocam 2 camera, also with a special electronically shuttered chip. So we tried to speed them up, and that camera arrived in Durham in September. We shipped it. We integrated it with our system, very flexible system, so we were able to integrate it in a week, and we shipped it on towards the end of September and went on Sky a couple of weeks after that. So we had this camera in the lab for a week, and then shipped it and went on Sky. So that was very quick, and that shows the flexibility of the system, that we're able to integrate cameras so quickly. We also have, with Canary, we have a number of DMs. One at the moment, another one coming, which we're using in the lab at the moment, but which will be a tweeter system next summer. And a tip-tilt mirror and a laser steering mirror. So we were on Canary on a server class PC. It's a fairly standard system. A number of PCI Express cards for the serial FPDP pixels, a gigabit Ethernet card for the Bobcat pixels for the figure sensor, a 10 gig Ethernet card which we use to get pixels from the Ocam camera, a GPU which at the moment is unused. We don't need it, but it's there if we decide we want to do something fancy in the future. A DM controller card, which does the woofer, the tip-tilt mirror, and the laser steering mirror, and then a second DM controller card, which will be for when we go on Sky next summer. We also have another PC, which is used as a file server and a gateway and runs various daemons, and a workstation where we do our tomography calculations, calibrate the system, control the system. So that's the setup of Canary. Tends to go on Sky at WHT twice a year. Because of the weather, we try and have summer months, October being about the latest we'd want to go. So we've used a number of different algorithms on Sky. I think Canary, it's probably fair to say that Canary is the world's most advanced AO system. Certainly got the most wavefront sensors and has tested the most different algorithms on Sky. So, for example, some of the things we've used, we have a brightest pixel calibration, where in each subafter you look at the pixels in each subafter and you say, all right, I'm only interested in, say, the brightest 20 of those, and the rest I'm going to say are noise. So then we are able to calibrate our system based on just 20 brightest pixels in each subaperture. We have an advanced algorithm for removing noise within these subapertures. We can track spots. So this figure here you see is, again, just an on-sky screenshot. You can see the subapertures outlined in blue, and they're not quite regular. You see the grid isn't quite regular, and that's because they're tracking the spots around. We can do correlation wavefront sensing, match filter, center of gravity, all the basic things like that. We have a slope linearization algorithm, which, because slope measurement on a pixelated detector is intrinsically not quite linear, so we can linearize our slopes if we need to. We've also tested a lot of different wavefront reconstruction algorithms on Sky with this system. Standard that we use is an MVM reconstructor, which is usually minimum variance, learn the fly algorithm developed by Eric Gendron from Paris Observatory. We've tested some scowl reconstructors, Cure, which is a very fast order n reconstructor. Neural networks, we've used neural networks to do reconstruction. LQG, the Kalman filter, again developed by some people in Paris. Preconditioned conjugate gradients, and as last night, a new one to add to that list, which I haven't added. So, what is this real-time control system? The real-time control system, DARC, is made of several components. It has a real-time core, has a control subsystem, a telemetry subsystem, real-time displays, and various clients. So the real-time core sits down here. Everything communicates with shared memory to this core. Have a control interface, telemetry system. That's on all of this is on one PC, and then on various other PCs spread around. It's all networked, and you can talk to them using Corba, or I'll come to in a minute, any other communication middleware that you like. So the real-time core is written in C. Importantly, it can't be blocked by any of the other processes. So the control process can't stop it. It will just continue going. There's no mutexes that it tries to get hold of or anything like that are external. It can't be blocked. And that's very important for a real-time control system because you need it to be reliable. So to control this system, it uses shared memory. So There's a double buffer parameter interface in shared memory. You write new parameters to one of these buffers. You tell a real-time system it wants to use those buffers. It switches buffers, uses that one. You then, when you want to change parameters again, you write to the other one. Telemetry, which is come to in a minute, is written to circular buffers in shared memory again. So this is things like your pixel data, calibrated pixels, anything that the RTC produces that might be useful to other systems around the telescope, whether it's to look at on a screen, whether it's to do orthogonal, anything like that. They're all written to shared memory, which then, of course, you're free to read and access as you wish. There's a GPU pipeline available in this. It's not essential. We are able to reach, with a single GPU, we're able to reach 500 hertz for an ELT-scale system. The real-time core itself is fully modular. I'll talk about this next, I think. Modules that can be loaded on the fly, and it's optimized for low latency. So modules include, you have modules for camera interfaces, modules for DMs, modules for calibration, for slope calculation, for reconstruction. So if you want to change one of your algorithms while you're on Sky, you can just unload one of these modules and load a new one in. We have actually changed some, and it's useful for development as well. If you're in a lab, you realize there's a bug, you can recode it without having to stop your system. You just unload the module, load the new one, and on you go. We can unload and load modules while the loop is closed. So that gives potential for quite a lot of flexibility there. Latency. Okay. I said it's optimized for low latency. What is latency? It's a delay between the wavefront sensor exposure ending and the DM taking its new shape. The longer that delay is, the more time the atmosphere has had to change, the more out of date your data will be. So low latency is critical for a good high-order AO system performance. And if you've got the right architecture in your real-time control system, you can reduce that. So if you want high latency, this is one way you can do it. You can expose your camera here. Now, most AO wavefront sensors tend to be frame transfer devices. So you expose your camera for a certain length of time, you do your frame transfer, you then do your readout, which takes a bit of time, you then process your data, and you set the DM. And your latency here is this from here to here. It's the end of the exposure to when you set your DM. Okay, that looks fine. But of course, we can do better than that. If we interleave processing with readout, so once we've read out a few pixels, we can actually start processing them. Read out a few more, do some processing. Read out a few more, do some processing. And that allows us to fit most of our processing in to within the period that the camera is being read out. And then once the camera is finished reading out, we can finalize our processing, which shouldn't take long, so we've done most of it, and set the DM. And that reduces the latency. This, of course, doing this adds complexity, but does give you, it's worth doing. If you can do it, it's worth doing. It gives you a significant gain in air performance, particularly when you've got, in certain atmospheric conditions, when you've got fast turbulence blowing across, things like that. But it does require a camera with a streaming interface. Most cameras, a lot of cameras will only allow you to get a whole frame of data at once. So you need to do something special to be able to get this access to this pixel stream. I've said most of the things there. So FPGAs and DSPs are well suited to this pipelining because the way they read cameras, in an FPGA you might not have enough memory to store a whole, well, certainly the older FPGAs wouldn't have enough memory to store the whole camera frame, so you actually need to process it on the fly. So the pixels stream out from the camera, flow through the FPGA on the DSP, and you do your algorithms and set your DM that way. Of course, algorithm implementation is a barrier here. It becomes very difficult if you want to add more complex algorithms. So if you want to do adaptive windowing or spot tracking, something like that, follow your spots around, in FPGA that becomes very difficult because you then start to have random memory accesses, which, okay, it's doable, but it's more likely to cause problems. PC approach, on the other hand, doesn't really encourage this pipelining. It's easier to deal with whole images, take an image and then process it. That's the way that PC processing generally is done. But it is possible, and does have a benefit. So DARC is pipelined in this way. DARC is able to do this. So it's able to takes data as soon as a sub-aperture has arrived. It takes that data, processes it. Single thread then processes all that data. It does the calibration, it does the slope calculation, and does the reconstruction from start to finish. Rather than having some threads doing calibration, some doing slope calculation, and some doing reconstruction. If you do that, it means that one of these threads have finished their calibration. They have to talk to these threads doing the slope calculation. Then they have to block and talk to these threads to do the reconstruction. And that way you've got lots of blocking points, which will add your latency. So the way we do it in DARC isn't like that. One thread takes all its data from start to finish. So that allows us to reduce latency. And even with novel readout architectures, so if you've got CCDs with many readout ports where the pixels arrive in strange orders, we have the flexibility that we're able to process in this way. Jitter. Jitter is also very important for an AO system, more so for some types of AO system nodes. It's the variation in latency. So on an FPGA, you can be fairly certain you'll have very low jitter because it's deterministic. You'll know the pixels arrive in your process and you know how long it takes. With a CPU system, that's not necessarily the case. The operating system may have other things to do. They have to go and service interrupts, do other things like this. Small jitter is usually a small fraction of an AO error budget, but of course it can destroy extreme AO performance. So if you're trying to find a planet next to a star, and you have a jitter event, it can allow the light from the star to flip onto where the planet is and completely swamp the signal. It's 10 to the 10 fainter. So it's essential to avoid large jitter events. And a real-time operating system, if you have a real-time operating system, it will give you about 10 microseconds of jitter. For Canary, with our 9 wavefront sensors, depending how we measure it, we're somewhere between 10 and 20 microseconds of jitter, RMS. And of course, a system with fewer wavefront sensors, you'll have less jitter because there are fewer interrupts to serve and things like that. So, the control of DARC. Now, this is the same diagram that I had a few slides back. We've talked about the real-time core at the bottom. We're now talking about this control interface here. How is DARC controlled? Okay, so we have a control server that sits between clients and the real-time core. The server basically speaks to the real-time core by writing parameters into the shared memory buffer. The default control server that we use most of the time is written in Python and uses a Corba middleware. That's an industry standard messaging system for client communication. It's easy, although because it's a modular system, you can easily take out that control server and insert another one. So we have a couple of other ones implemented that we use sometimes. And of course, it's easy to add and replace with a middleware of your choice. So if you've got a middleware that's your own middleware that you like to use, maybe it's a standard for a telescope or something you're used to, you can write your own control server for that. Telemetry. So telemetry is, that's this box here on the side. I've been told I should use my pointer rather than point. There's a telemetry system. So this is access to all the data of interest that's produced by the real-time core. So calibrated pixels, are you doing your calibration correctly? Slope calculation, well, you might need your wavefront slopes for optimizing your control algorithms, things like that. Reconstructed phase, you want to know what your DM is doing. Flux in each subaperture. Are you missing flux? Has your guiding stopped working? Are you only illuminating half your subapertures? Things like that. And what shape the DM is actually taking. So this data is of interest, and you want to send it out to the clients. It can be spread all around the telescope, possibly all around the world. So the default module that we have for telemetry is Ethernet sockets. It's designed to be simple, easy to use, reliable. Just node to node, send data from one node to another. Within a node, you can use shared memory within a node. So we only send data once to each node, and any clients that are on that node access it from shared memory. Of course, again, it's modular. This telemetry system is easy to replace with a middleware of your choice. There's the option to receive every frame. So if you're doing something with wavefront slopes, you probably want every frame. Or to decimate this data. So if you're looking at your wavefront images on the screen, you only need them at 30 hertz. And your AO system might run at 300 hertz. So you only want every 10 frames, things like that. And the telemetry, it's important that it can be synchronized. So you can receive, for example, DM demands and wavefront slope at the same time, so that you know exactly what was happening in your system then. Clients. We have many different clients. None of these are essential. None of these are an essential part of the system. They include an engineering GUI, that's seen on the left-hand side. Real-time displays. Now, this one at the top here is a real-time display. What happened there was we were, this was again taken on sky. So we had our AO system was on the star. We wanted to take some background images. So we moved the telescope off the star. Of course, then the wavefront sensor wasn't seeing anything. So it was just looking at noise. And the adaptive windows that we had tracking the spots were then just moving around randomly with noise. Now, if you think about what's going to happen there, these are going to move around. Eventually, two of them might join together, lock on, then they'll be following the same bit of noise all over. And eventually, all of these things will just lock on, and we just have one move around. So what we can do is we can limit the range of motion that these boxes move. And so you can see roughly there's some sort of grid. You can just about see it. A grid is still there of how far they're allowed to move. And of course, when we move the telescope back to the star, in less than a second, they've well, we don't notice it's instant on the display. All these selectors are back tracking the spots as they should be, and we then close the loop. The plot on the bottom here, this wiggly, let's go back. This wiggly line is the same real-time display, just configured in a slightly different way. It's a very flexible real-time display system we've got. This is an autoguider for Canary here. It tells the WHT when it reached the guide. And a camera calibration tool at the top there. Documentation. There is, of course, documentation for a system like this. May not be brilliant, but it's there. 44-page user guide, an API reference manual, a developer's guide. Lots of hardware currently supported, a whole list of cameras that we use, some in the lab. We also use this for science cameras, so that we're able to get the whole system of Canary is using the same interfaces for all the different cameras, and interfaces for lots of different DMs as well, which have been developed over the years. And all of those are plug-and-play modules that we can load into the real-time system or take out as needed. It's a system that's suitable not just for one type of AO system, but for all different AO system types. SCAL, we tested on Sky, of course, with Canary. XAO, we have an XAO system in the lab in Durham. Wild field AO systems, the only one of these that we haven't tested with Canary on Sky is MCAO, because we don't have mirrors conjugated at height. Can be used for solar AO, biological AO as well, vision science, and that sort of thing. So wide field AO is where you have multiple cameras, multiple guide stars. You're able to do a tomographic reconstruction of the atmosphere where these layers overlap. So we have some guide stars up here. Lights coming, these are probably lasers because they're green, coming down through the atmosphere. Where the light from these stars overlaps, you're able to reconstruct and work out what the atmosphere is doing at these points here. So several wavefront sensors. These go to your real-time system, reconstruct it, a DM, tip tilt, and a science image. So because you've got lots of cameras, it means you have lots of interrupts to service. You have to think about your memory bandwidth. Pixel data tends to be fairly large, coming fairly rapidly. Can that be spread through the system reliably? Solar AO. Solar AO has different demands for real-time control than nighttime AO. One of the main differences is the type of wavefront processing that they do. Rather than using center of gravity, they have to use correlation. So that's a typical image from a solar AO Shack-Hartman solar. And how do you center of gravity that? You can't. You have to use correlation. You correlate where it was with a fixed reference, and that tells you what your wavefront slope is at a particular time. They generally have higher frame rates, but fewer structures than nighttime AO usually. And the processing demands here are dominated by slope calculation. So it takes a lot of processing to calculate the slopes. Once you've got them, the reconstruction is a much smaller part of the computational burden. ELT-scale operations. Well, for the European ELT, there will be likely to be 6 laser guide stars, up to 5 natural guide stars, each 80 by 80 subapertures, so that's a lot of subapertures. The LTAO, SCO modes will have 1 DM, 3 DMs for the MCAO, up to 20 DMs for MOAO systems. Frame weights varying. And at these scales, it's the wavefront reconstruction that becomes challenging. The memory bandwidth that you need to do a conventional matrix vector multiplication scales as telescope diameter to the power of 4. So you can see going from a 4 meter to a 10 meter to a 40 meter, your memory bandwidth requirements scale quite rapidly, and that then dominates the computation. And that's where the memory bandwidth of GPUs comes in very handy. CPUs can't really do that unless you have a large cluster, but then you have all sorts of problems with synchronizing this data, spreading it around the cluster and so on, with very low latency. So GPUs for the ELT are a favored option. Can be slightly problematic for data access. Getting your data into a GPU has, to date, been one of the major problems here. But, for example, with DARC, we can demonstrate SCAL, ELT scale with 1 GPU, reaching about 500 Hertz, and that's with real camera data going into the system, being processed, and then DM demands coming out. So for an MCO system, for the ELT, probably 6 PCs with some GPUs would do the job. Estimating real-time control performance. Okay, so if you have a system that you know you want to build, how do you estimate the performance that a real-time system is going to give? You've got some specific hardware in mind, or you want to be able to spec your hardware. How do you do that? There's no good way to do this. You can't just look at the problem and say, all right, my pixel data has this many pixels, and it's coming in at this rate, so I need that much bandwidth. My reconstructor matrix is a certain size, needs certain bandwidth. You could put something together theoretically. You'd be wrong. There are too many factors that come into play for an AO system. All things like interrupt handling, feature creep. You know, when you're specifying your system, there's probably something you've not thought of, that when you specify the hardware, you realize we didn't include that, and that's going to slow it down a lot. Hardware no longer meets the specifications. So really the only way to do this is to build a system and benchmark it, see how it performs. You won't get a realistic performance estimate any other way. So the way to do it is to build a system. But then, of course, to build a system, you need to know what you can do anyway. So probably the best thing here is to use an existing system, preferably one that actually you know works on Sky. And that way you can be sure that the performance that it gives are those that are going to be used, that you'll be able to achieve on Sky. So performance optimization within DARC, there are many ways to tweak the performance. Primarily, it's by adjusting the number of CPU threads that are used. So if you're running it on a laptop, for example, which doesn't have many cores, you'd only want a small number of threads, because the more threads you have, the more time you have to spend, more inter-thread overheads there are. If you've got a large server with maybe 32 cores, you can use many more threads and still get benefit. Where you put those threads, on which cores, and what priority you assign to them is also very important. So if you've got some threads that are responsible for reading data out of the camera, you want them on the core to which the PCI bus is attached, for example. How do you process these threads in DARC? Well, I've said that each thread processes subaperture from start to finish. If you allocate certain threads to certain subapertures, it stops a bit of randomness going on. It means that each thread knows it's going to do a certain number of subapertures, and then it reduces your jitter and probably your latency as well. If you consider your control matrix size, if you have if you make your number of subapertures a multiple of 4, for example, it means your code will vectorize much more nicely. So you might have to add some additional rows to control matrix so that it can vectorize. Though, of course, if you're doing that, I would say you're probably better just buying a slightly faster computer, because it's usually easier. And, of course, you can use real-time kernel, which will reduce jitter. Now, a lot of people think that a real-time kernel is probably slower. I found that not to be the case. They tend to be faster because, certainly for AO, because it means that when you're processing your data, those threads are always doing processing. They're not getting interrupted by other threads, and so you get your processing done quicker. And then in downtime, where you're waiting for your next frame, your next pixels to start arriving, then the operating system can do what it needs to do during that time. So real-time kernel probably a good way to go. Real-time simulation. Now, DARC has the ability to interface with an AO simulation. And look, basically to do this, what we do is we can load a different camera module, a simulation camera module. Actually at the moment, it's one that just opens an Ethernet socket, and the simulation can then send wavefront sensor data into the real-time system and receive DM demand out from the real-time system. We can flip between simulation and on Sky. Now, of course, I call it real-time simulation. The simulation itself doesn't run at real time, unless it's a very small system. Here, I mean, you're using a simulation with your real-time system. So this allows you to develop user tools before your bench is ready. You can set up a real-time simulation system. It all runs in a computer. You can then develop your end user tools, all that sort of stuff, before you have anything concrete on the bench. Allows multiple developers to work simultaneously. You can have some working on the bench, others can test an algorithm standalone on the computer without needing access to the bench, speed things up. Allows us to test and develop algorithms and concepts. Okay, so you've got an algorithm that works in MATLAB, and you want to use that on Sky. So you code it into your real-time control system, but have you translated it correctly? Are there bugs in there? A real-time simulation allows us to test that. Allows us to verify the performance of the AO system. You can put in, if you use the simulation, you know at what height you put your turbulent layers in. You can then find out whether your AO system is performing, the real-time system is performing, doing its reconstruction as you would expect. So it's a very powerful tool. It's one that we use with CANARY. So CANARY simulator is a high-fidelity simulation of CANARY on DHT. It goes into details like wavefront sensor pixel scales. So different wavefront sensors, the LGS and the NGS all have slightly different pixel scales. They're all rotated different ways as well. So that's all in the simulation. Guy star flux, positions of these guy stars on Sky, misalignments and so on. So we use this simulator with the CANARY Control GUI. This is just a screenshot of the CANARY Control GUI. It's not part of the real-time system. It's just a user tool that we use to control the whole system. And this GUI doesn't know whether we're in simulation mode or on Sky mode. And a simulation is of high enough fidelity that we can produce a control matrix in simulation, and then if we accidentally go on Sky with that control matrix, we manage to close the loop. Performance probably isn't quite as high as it should be, which makes us realize that something is wrong, but it shows that the simulation is fairly high fidelity, so it's able to simulate the real system very well. So this is just a screenshot of CANARY taken from a few hours ago. So what we have here is lots of wavefront sensors, really. Raw pixels are in this bottom one here. There are, where's my article? There it is. Right. So this screen here is our raw pixel data for natural guy stars. Here was our LGS wavefront sensor. It's got a feature which is a very bright line through the middle of the chip. And so the wavefront sensor data is actually here, but scales that you can't see it because of this bright line, which we're going to send the camera back to see if we can get that fixed. True sensor here. Now, calibrated pixels of the laser guide stars are up here. So the line has been calibrated out. That went through here. This is our science PSF. DM demands, different wavefront sensors. You see the spot tracking going on. So that's just a screenshot of some on-sky operation. And you see we were closing the loop. The seeing wasn't great. This was one of our wavefront sensors. Spots kind of everywhere. And at some points, we just looked like a donut. Anyway. So what's the relevance of all this for a system like Granticam? Well, Granticam are designing a 20 by 20 Slapture SCO system. The real-time pipeline for DARC, we're able, on a laptop like this, to be able to run on a 20 by 20 scale system at 2 kilohertz. That means that with this system, you're easily able to meet any requirements, modest hardware, and an existing code base. So it's on Sky ready. It's also extensible for future systems. So if in the future there were plans for a GLAO system, now the Palmer, of course, is very ground layer dominated. GLAO system will give you excellent wide field of view performance. Real-time system DARC works with GLAO. Also works with XAO. We've demonstrated on Sky fast order n wavefront reconstruction. Wide field AO also works there as well, all with the same on Sky tested real-time core code. And that can give significant cost reductions rather than developing one system for SCAL and then later coming along and developing another system, another AO system type. It's all there, it's all together, all the interfaces will be the same. So, in conclusion, I've introduced DARC to all. I hope you have liked what you've seen. It's a flexible, modular, open source real-time control system. All the components of this system are replaceable. So if there's a part you don't like, take it out, put your own in. It's high performance, low latency, suitable for all AO system types, and has been tested very thoroughly on Sky. Thank you.
Okay, so thank you so much for your talk. Is there any question? Yeah, there.
The real-time processes need some special programming, or is just because you're using some real-time kernel behind in the operating system?
It's just real-time kernel. Yeah, the rest is all in C. I mean, there are techniques you use when programming C to optimize the performance, like how you block your threads, things like that. But it's all standard C.
So.
Well, I understand that in the system for wide field AO,
yeah,
you may be able to retrieve the location of the layers of the turbulence. So you may be able to get a sort of turbulent profile. So would it be any advantage of this system if you would know in advance what is the height of the layers and how many do you have?
Yeah, it certainly does make a big difference. So one of the steps with CANARY that we do is before we close the loop, we take some data, just open loop on Sky data, take the wavefront slopes, and then from that we can work out covariances of where the different layer heights are. We also usually have a SIDAR system going at the same time, which gives us these profiles. So it's essential for a wide field AO, it's essential to know where your layer heights are. We need to know them typically to a resolution of about 1 to 2 kilometers. For an ELT, they'll need it to a few hundred meters, but for us, a few kilometers will do.
You mentioned that it is possible to introduce new reconstruction algorithms, develop or program in MATLAB, Yorick, or any other language, but they need to be translated.
That's right, they need to be translated, yeah. So you can, so an example of this was when Austria joined ESO. Part of their joining contribution was a lot of staff effort to develop new algorithms for AO. So some of the algorithms that they developed were wide field AO reconstruction algorithms, mostly done in MATLAB. They became interested in testing them on CANARY, so they translated them to C. We then encoded that into one of these modules, and we're able to load that into the system to test it on Sky, which was that, for example, was one of the things that we were testing last night. But they had to be translated into C. But it was essential then for us to use the real-time simulation to understand that if we'd have just gone straight to the bench, we wouldn't have had a clue what was going wrong. So it was essential to use this simulation with the real-time implementation of the algorithms to work out where the mistakes were, where the misunderstandings were, and so on. So that was very useful.
What is the support that you needed now, for instance, the William Herschel?
Yeah.
How many people do you have to operate this? I mean, how does it work in practical?
Well, it's not a facility instrument. It's just one that we bolt on for twice a year, 6 nights at a time. We can run the system with 2 of us. Typically, there'll be 3 or 4 of us. We usually have a PhD student with us, you know. So there's usually one of us controlling the lasers, making sure they're tracking okay and not getting lost and not colliding with science observations from other telescopes. And then another person doing the tomography and calibration system and so on.
For example, in what you propose for GTC.
Yeah.
I mean, now I understand that you are still making experiments on the system, and because of that you have these PhD students and all that.
Yeah,
but with time, I suppose that a basic model or something like the thing you have said regarding GTC, would it be something that could be operated by just the telescope operator, the support astronomer?
Easily, and particularly, I mean, one of the difficulties we have is doing tomography. We're doing experiments with atmospheric tomography. If you've got a SCAO system, it's almost push button. You know, it's very easy. You have a control matrix that you take on a bench, you load that in, and you click go. So that, you know, we would easily we could actually run the system with one person, though it would be quite demanding for that person because they'd always have to be checking different parts of the system. But for SCAO, it's much easier.
Okay, so if there are no more questions, let's thank again Alastair for being here.